Okay, welcome students to your first lecture of the school year. So the first unit that we are studying is experimental design. We're essentially looking at how to set up an experiment and all the skills that are needed for that. So our first conversation is going to be about the scientific method. We're going to look at the different steps of a scientific method, see how scientists set up different experiments and why they do it, and what they do with the results that they find. So let's get started. So the scientific method is the process of solving problems and making discoveries. This flow chart is showing all the different steps of an experiment, from the very beginning to the end, if you can call it that. So the first thing that a scientist needs to do is ask questions. Ask questions about either observations of the world around the scientist, or ask questions about something that maybe the scientist was reading. The scientist needs to then conduct some background research, construct a hypothesis, test with an experiment, analyze the results that are collected from the data that the scientist receives from the experiment. If the hypothesis is true, the scientist reports the results. If it proves to be false or only partially true, then the scientist goes back to the drawing board, constructs a new hypothesis, designs a new experiment, and starts all over again. So let's take a look at each step. So the steps of the scientific method are: first, ask a question. Do background research, construct a hypothesis, test with an experiment, collect and analyze the results, draw conclusions, and then report the results and revisit the hypothesis. All right, so let's start with the first step of the scientific method, which is asking a question. Before you can start any experiment, you must first identify the problem and ask a question that it may aim to fix. We aren't always fixing things by conducting experiments. Sometimes we just want to know more. For instance, a lot of scientists are curious as to why do we need to sleep. That's a long discussion, so I'm not going to get into a lot of it, but essentially it doesn't make evolutionary sense that animals need to sleep because it puts us at risk of becoming dinner, but yet it's something that we have to do. So scientists want to know why. But sometimes then we want to fix problems. For instance, it's becoming more and more common that bacteria are becoming resistant to antibiotics that we need in order to become healthy. Scientists are trying to find out why and how we can work with that. How can we create medications that bacteria can't become resistant to? So this gives a purpose for conducting the experiment. The next step is to conduct some background research. Background research helps scientists to gather any data that has already been collected by other scientists through experiments that they may have collected. Sometimes scientists come up with a question, and they may think that it's a very novel question that no one's ever asked before, and they go to conduct some background research, and they find that there's actually been lots of experiments already conducted on that question. What it does is it helps the scientist to come up with some preliminary observations. So these observations are often what lead a scientist to ask the questions in the first place. So before we talk about observations a little bit more, let me explain what the background research does. Is it allows a scientist to understand other experiments that have already been conducted, to know what the results of those experiments are, and to see what further experimentation needs to be conducted for that particular question. So what is an observation? What's the difference between an observation and an inference? Well, observation is information you can gather using your five senses: touch, see, smell, hear, and taste. These are fact-based. They are not opinions or guesses. So, for instance, say for whatever reason, no one ever told you that when the heat ring on a stove is red, that means that it's hot and you shouldn't touch it. So you see this heat ring on an electric stove and it's red and it looks really pretty and you want to touch it and you do touch it and your skin burns and you're in pain and you realize that it was hot. That's not an opinion or a guess. It's a fact that that stove is hot and it burnt your skin and it was painful. An inference, on the other hand, is an explanation of the things that you have observed. So you observed that hot a stove. I'm sorry, let me reword that. You observed that that stove was hot. So the next time you see an electric heat ring that is red, you're going to make the inference that that heat ring is hot and you better not touch it. So this inference is now based on a past experience. However, your inferences can change based on more observations. So sometimes, for different reasons, people will set up model stoves. Maybe they're trying to sell the stove and they want to make the stove look more appealing and demonstrate that it does in fact get hot if it were turned on, plugged in, turned on. So they'll they'll paint or put on a cover on one of the burners that's actually red to make it look like it's producing heat. Now, if you've never actually encountered a model stove before, you may not know that that red burner is not hot because you don't have a past experience on it. But somebody comes walking by, they laugh when they see the red burner, they touch it, they continue to laugh, you realize they didn't get burnt by it, so you touch it yourself, and you can see that it's just a model. It's not actually hot. So your inference has changed, and you can understand the difference between a stove that is actually hot and a stove that is just a model. Alright, so now that you've asked your question, you have done your research, you're ready to construct a hypothesis. A hypothesis is a prediction based on observations. It's an educated guess about what you expect to find in this experiment. In other words, what do you expect to happen? It is often written in if-then statements. In this class, it is always written in if-then statements. If I touch the stove when it is hot, then my skin will burn. A hypothesis must be testable and it must be repeatable. Alright, so you have your hypothesis. You're now ready to design your experiment. Before you can test an experiment, you have to design it. The experiment is designed to test the hypothesis that you have come up with. An experimental design alone is not the scientific method. It is only part of the scientific method. It is one step of the scientific method. So the design includes a title, a hypothesis, the procedures, a list of all the steps that are needed to conduct the experiment, materials, all the supplies you need in order to conduct that experiment, observation and data. So you're going to need tables or charts to collect the results of the experiments. And we're going to be going into a lot more detail about how to design experiments in class. Alright, so let's talk about variables. So for a complete experiment's design, you need to identify independent variables, which are variables that are being purposefully changed by an experiment. So for instance, if I want to know what is the ideal amount of fertilizer for growing a particular type of plant, let's say a gardenia, then I would set up an experiment where I would give 4 different gardenias different amounts of fertilizer. That fertilizer is my independent variable because it's what's being changed by me, the experimenter. The dependent variable is the variable that is being measured. It's responding to the independent variable. So in my plant example, I would be measuring the growth of the gardenia plants. How much the gardenia grows depends on how much fertilizer was given to the plant. Another example is to investigate how different weights affect the length of an elastic band. So you decide the weight to apply. This makes the weight the independent variable because it's what you're changing. You measure the resulting length of the elastic band. So the length is the dependent variable because it's responding to how much weight is added to the elastic band. And then you test with an experiment. For a complete experiment's design, you also need constants, which are factors that the experimenter hold the same throughout the experiment. And then you also need controls, which are the standard for comparing experimental effects. This is what you would normally expect to see. So if we go back to the plant scenario, a constant would be that all the gardenias are grown in the same type of soil. For a control, think of a control as a baseline measurement. So in my plant scenario, I need a gardenia that's receiving no fertilizer. And I need to compare the growth of that gardenia with the growth of the gardenias that are receiving fertilizer. You also need a number of repeated trials. In any experiment, the minimum number of repeated trials is 3. If it's less than 3, then you're leaving the results up to random chance. So let's go back to our rubber band example. The constants are to use the same elastic band all the time, the same scale. A control would be the length of the elastic band without any weight. All right, so we need to collect data before we can draw conclusions. This data should be recorded in the charts that you have already designed. You need to analyze that data. This involves interpreting the data that you have collected, and you use tools such as graphs or statistical calculations in order to identify any trends. Graphs are a great way to analyze data because it gives you a quick visual snapshot of the data that you've collected. You need to compare the different experimental trials with each other. All right, and finally, you're ready to draw some conclusions, which are logical deductions of the data. So it's looking at a graph and being able to say, oh, well, based on what I see in this graph, this is what I conclude from the experiment. So in other words, does the data show you how to explain the results of your experiment in a summary? And to identify whether your hypothesis is supported or not. All right, so did the data or evidence support the hypothesis? If so, you accept the hypothesis and you publish the results. Publication is key because what that does is it gives the information of your experiment to other scientists. Those other scientists can then use your experiment to conduct their own experiment. Essentially, they will be repeating your experiment to see if they come up with the same results. If many scientists are able to come up with the same results, then your results are considered to have validity. So this is the part of the flowchart. We analyze results to draw conclusions. If those results support the hypothesis is considered to be true, and then you report your results. If data or evidence does not support the hypothesis, even if a part of the data supports the hypothesis, the whole hypothesis has to be rejected. Hypotheses are black and white. The data either supports it or it doesn't. Even if your data supports part of the hypothesis, you have to state that the hypothesis was not accepted. So we can look at this flowchart here, and you can see that the second part is if the hypothesis is false, the scientist needs to go back think about why the hypothesis was not supported, and then based on that information, construct a new hypothesis, design a new experiment, and then publish the results. And it starts all over again. So what happens if the hypothesis is rejected? Is a scientist done if the hypothesis is accepted? No, they start again. That's the process of science. Science is a continual cycle. Okay, that's your first lecture. I hope this was informative, and we will talk more about this in class.